Math 1314, Tyler Junior College, Section 3.4, Zeros of Polynomial Functions. Finding zeros of f of x, Example 1. In the previous video, we developed the rational zero theorem, which said I can make a list of rational numbers, which includes integers, that might be zeros of your function. But how do we find which ones they actually are, and what do we do when we find them? Well, we're going to answer both of those in this first example. Find the zeros of f of x equals x to the third power plus 2x squared minus 7x plus 4. You may recognize this function as one of them from the previous video where we listed the possible rational zeros. Just as a reminder, to make the possible rational zeros, you start with factors of the constant term in the numerator. The constant term was 4, and so its factors are plus minus 1, plus minus 2, and plus minus 4. And in the denominator, factors of the leading coefficient. Since the leading coefficient is 1, its only factors are plus minus 1. Then we made every possible ratio by choosing a numerator and denominator. Since the only denominator is 1, our ratios were 1 over 1, 2 over 1, and 4 over 1. And each one was plus minus. But in this case, I'm not going to write plus minus in front of all of them. I'm going to list the negatives separately. You'll see why in a minute. Those are the numbers that might make this function equal to 0. If you're finding the zeros, your next step after listing the possible rational zeros is to use synthetic division to locate an actual zero. Because all we have now are numbers that could possibly be zeros. We want one that actually is. And remember, we're using synthetic division because the remainder theorem says that we can use synthetic division as an alternative to substituting a number into a function. Instead of putting the number in the function, put the number in the box and run it through synthetic division. The remainder at the end will be the value of the function. Second, if we find a zero, we want to use synthetic division anyway to get it factored. So once we find a zero of the function via synthetic division, we already have the work to get the function factored. Now, how do we locate an actual zero? Well, you set up a synthetic division problem using the function as the top row, the coefficients of the function as the top row, so 1, 2, negative 7, and 4 coefficients of the function. Then you pick one number from your list and stick it in the box. And hope by the time you get to the end, you have a remainder of 0. Now, every list will contain 1, and it will usually be written first. And that's what people will normally try first. I'm not going to try one first, just to point out that you don't know which one it could be. Maybe it's negative 2. You'll know if negative 2 is a good choice if we have a remainder of 0. So let's go through the synthetic division, remembering how it goes. Bring down the first number, multiply diagonally by the box. 1 times negative 2 is negative 2. Add 2 and negative 2 is 0. Multiply by the box. 0 times negative 2 is 0. At this point, I can tell it's going to fail, but I'm going to go ahead and finish the work. Add to get negative 7. Multiply by the box. Negative 7 times negative 2 is 14. And finally, we add and get 18. This is not 0. We want 0. So what does this mean? It means negative 2 is not the number that we're looking for. This is why I separated the positives and negatives so I can cross out numbers as they failed. And eventually, hopefully, you'll run into one that works. And I say hopefully because there is no guarantee any of them will work. However, you won't be given one where none of them work because, well, we couldn't finish the problem. So let's try 1, which normally I would have tried first. But I wanted to point out that once you try a number in the box and it fails, you cross it out, it's gone, no good. But if we try 1, in the box, and the top row is still the same, 1, 2, -7, and 4, I believe 1 will work. Bring down the first number, multiply by the box. 1 times 1 is 1. Add to get 3, multiply by the box. 1 times 3 is 3. Add to get -4, multiply by the box. 1 times -4 is -4, and finally add. Hooray! Remainder of 0 is what we want. Because remember, if you have a 0, that means 2 things. Putting 1 into the function will also give you 0. Remainder theorem says that. Just like putting -2 into the function will give you 18, remainder theorem, putting 1 into the function will give you 0. So at this point, we know that x equals 1, the number we put into the box, is an actual 0. So this is like in the last video of the previous series when I said find the zeros. By the way, here's one of them. I wasn't given one now, but I found one. Now we're going to do the same thing we did before, except we kind of already done the work. What we did with the 0 that we knew is turned it into a factor, which turned it into a division problem that gave us a remainder of 0. But we already had the division problem. We used it to find a remainder of 0. Now we can use this division problem to help us factor. So your last move is use the successful synthetic division problem. And by successful, I mean the remainder was 0. Use the successful synthetic division problem to factor f of x. Because remember, if the remainder is 0, you found 2 factors. One factor came from the divisor, the box number. Before I do that, let me write the original function. X to the third plus 2x to the second minus 7x plus 4. We're finding the zeros of that, so we're putting it equal to 0 and solving it. One factor comes from the box number, but remember, when you move the number from the factor to the box number, it changes signs. Anytime you move a number in or out of the factor, it changes signs. So if I put this 1 back into the factor, it changes back to a -1, and so the factor was x minus 1. The other factor is from the bottom row of the successful synthetic division problem. Just remember that the degree gets lowered by 1. This was originally a 3rd degree polynomial, so the quotient will be a 2nd degree polynomial. This one represents 1x squared. Then just lower the powers. 1x squared, positive 3x, minus 4. We have used the results of the successful synthetic division problem to factor the function. Now we're not out of the woods. We're still being asked to find the zeros of this function, find the numbers that make this equal to 0. All we've done so far is factor. And I know it's a roundabout way of doing it, but this is what I call the universal factoring technique. Does not matter how your problem is set up or how big the problem is. If you can find a 0, thanks to a good synthetic division, you can factor. 1 factor from the box, 1 factor from the quotient, the bottom row. Now, to finish this problem, and that'll be step 4, finish solving. Look where the problem currently is. We are factored and equal to 0. That means we just have to put each factor equal to 0. So moving it up here, we can put the first factor equal to 0, and we can put the second factor equal to 0. Now granted, the second factor is quadratic, but I'm not worried about that because I have ways of solving quadratic equations. The first factor gives us the 0 that we already located, x equals 1, but the second one's going to require some work. I'm just going to go ahead and use the quadratic formula on this because this won't factor. You might think it'll factor, but it won't. Give it a try. I dare you. Without dilly-dallying, the quadratic formula will give us -b, so -3, plus or minus the square root of something, I'll go pick that up in a minute, over 2a, so over 2 times 1, which is 2. Under the square root, we're going to have b squared, so 3 squared is 9, minus 4 times a times c, so minus 4 times 1 times -4. So, oh my gosh, this is going to factor more. This wasn't supposed to factor. That one. I'm sorry. B squared minus 4ac. 4 times 1 times negative 4 is negative 16. 9 minus negative 16 is 25. If the discriminant, the part under the square root, is a perfect square, this thing should have factored. I can't believe I looked at it and said it won't factor. We get negative 3 plus or minus, the square root of 25 is 5 over 2. So if we split that up, we get negative 3 plus 5 over 2, negative 3 minus 5 over 2. And so negative 3 plus 5 is 2, divided by 2 is 1. Negative 3 minus 5 is negative 8. Negative 8 divided by 2 is negative 4. Can't believe I got something that factored. So what this means is that our final answer is x equals 1 and x equals negative 4. I did not plan for 1 to show up twice, but it can. It showed up once there and it showed up once here. You could say x equals 1 with multiplicity of 2, meaning that it showed up twice, once here and once there. But if you're just listing the zeros, you only have to list it once. All right. And notice that negative 4 was in our list. We just didn't get to it. I'll be honest, I'm a little surprised that this worked out so nicely at the end. The reason is, and you may have seen this in a previous video, that I just made up a function whose 0 is 1. Not to retell the entire story, but when I built the function, I stopped here and said, all right, if I plug in 1 right now, what will I get? 1 plus 2 minus 7 is negative 4. Okay, so a plus 4, we'll cancel it. 1 is a 0. So when I randomly made the problem, I wasn't expecting this quadratic trinomial factor to behave, but it did. Imagine that. All right, so that's how we can use the rational zero theorem to help find the zeros of a function. It makes a list of things that might be good box numbers, and when we find one, we found 2 factors, one from the box number and one from the bottom row, and then we keep going. Now, I'd love to say that it's always this straightforward and convenient. I'd be lying, as you're about to see in the next video.